almost on schedule. We will move to a TSO-DSO coordination session, and the first speaker is Zejun, who will talk about pricing under generation and network scarcity.
Okay, so hello, my name is Zejun, and today we're going to talk about distribution, location, and marginal prices under generation and scarcity pricing. I don't know why the first slide is not on, but I think it's not ready. Yeah, I'm using the arrows currently. Yeah. Oh yeah. Okay. Yeah. Okay. So a little bit about me. I started my PhD pursuit this year at October when I finished my integrated master's at National Technical University of Athens. My research interests lie in renewable integration, congestion management, optimal power flow, TSO-DSO coordination, and etc. So why do we need TSO and DSO coordination? We have an increasing integration of distributed renewable resources, such as solar rooftops, and flexible resources such as batteries and electrical vehicles. So in the medium and low voltage grid, and this has motivated the TSOs to take an active engagement in short-term operations such as voltage control and locational marginal congestion management. Also, these distributed resources benefit both TSO and DSO. And as I said before, for the DSOs, it's voltage control and locational congestion management. As for the TSOs, it's frequency control, congestion management, and balancing. So here we have some existing TSO-DSO platforms in Europe that are on air right now. In total, there are 13 platforms, 7 pilot platforms, and 6 commercial. In Greece, currently, we do not have any, as far as I know. So now I'm going to introduce some basic concepts that I'm sure anyone here probably knows, but at what level we have contributed to these concepts. First concept is DLMPs, which basically are locational marginal prices at the distribution level. They're a very disciplined framework for TSO-DSO coordination. Professor Oren and Hale have talked about it in the past, and our contribution are the extension of DLMPs to account for reserve deliverability. The next concept is scarcity pricing, which is based on operating reserve demand curves, or in short, ORDCs. And it's an approach for remunerating flexible capacity through energy and reserve revenue streams. One of the pioneers, of course, was Professor Hogan, and our contribution to his work is our energy prices with reserve scarcity on a meshed network. Finally, it's the concept of reserve deliverability, which is the ability to deliver committed reserve in different parts of the network. Professor Karamanis, who I think is not here today, and Professor Zejun have talked about it in the past, and our contribution is that we propose an inscribed boxes model for reserve deliverability, which is applied to TSO and DSO coordination and generalizes to mesh networks. Basically, we generalized Professor Karamanis' model to a more computationally tractable one, as I'm going to present later. So in order to give you a better incentive of what problem we are trying to tackle, here I have a simple 3-node network example, where we have a BSP at node 1 and one reserve demand order from each node of 2 and 3. The line parameters are the same. So how should we? The first question that we want to answer is how should we allocate this? How should we allocate the reserve on this network? One who might not be in this room, because we are all very great, I think, would probably say that we might say that the worst scenario of activations of reserve is if both reserve demands activate. In this case, we're going to see a flow of 1 megawatt from node 1 to node 2, and a flow of 1 megawatt from node 1 to node 3. If this was the case always for the demand activations, this would pose no problem to our network. But in real life, TSO reserve demands may or may not activate, and the network should always be able to handle any pattern of activations. So to take this a step further, if only, let's say, the reserve demand at node 2 activates, we're going to have a flow of 2/3 from node 1 to node 2, and a flow of 1/3 from the long distance, node 1 to node 3 and node 3 to node 2. This clearly violates the line capacity that we have, making our network infeasible for the reserve that we allocated. So how much would actually be the reserve we allocate in this network? The answer is 1.8, which means that for the activation of both, we can have 0.9 to node 2 and 0.9 of reserve to node 3. And for the single activations, we're going to have 0.6 from the short distance of node 1 to node 2, and 0.3 from flow from node 3 to node 2. So to give you a more illustrative also example of how our model does what we just described, I have these figures here. So in the orange polyhedron, it is a set of feasibly reserved demand allocations when both reserve demands are fully activated. Okay, thank you. Okay, are fully activated. And in the blue polyhedron is the result of the inscribed boxes theorem that we apply in our proposed model. So we can see clearly that at point 1.1 that we discussed earlier, which is the allocation of 2 megawatts in total, it is outside of the feasible set of the inscribed box model. Yeah. So in general, for a network with n reserve demands, the number of activation scenarios that occur are 2 over n, resulting in an exponential number of constraints, which is actually intractable. So we exploit a result of computational geometry by Bemborat, which inscribes a box within a polyhedron without requiring an exponential number of constraints. The idea is to focus on the inclusion of the upper right corner of the box within the polyhedron. Basically, what this theorem does is that it accounts always for the worst scenario of activation pattern. Okay. So now I'm going to introduce the two models that we managed to match one-to-one for radial networks. First is Professor Karamanis' model. What is very interesting in this model is the state variable I, which states if a generator in the network activates or not its reserve for each scenario S. The objective function is actually a very simple maximization of social welfare function. Here in the first summation, we have discretized the an ORDC curve with L orders. Each order has a price PRL and the quantity that's cleared of TRL. The second summation, which is actually the cost of each generator producing energy. PU is the price of the generator, and P is the production of energy. Then we have the energy balance constraint, which we have the production of energy plus the production of reserve that's actually activated in the scenario S, plus the constants P and D, which are positive and indicate the positive injections or the negative injections at the node. And then we introduced a variable that's basically there to make our network feasible, because we have extra reserves activated and they actually consume the activated reserves. The reserve balance constraint is a very self-explanatory equation. And then we have the line then we constrain the flow of energy in our model. The variable f is, as we can see, for every line and for every scenario. So it accounts also for reserve flows. And the rest of the model are some linearized power flow equations and the maximum generator capacity limits. The difference to our model is that we introduce a flow variable for reserves, FR plus and FR minus here. FR plus are for the reserve flows from node to the to node. FR minus are for the flows from to node to from node. Also, we introduce a matrix A and this schematic here, which are derived from the result of the Bemborad theorem, which allows us to apply basically the theorem of the Bemborad to our model. Here are the tables that allows us to jump from one model to another. They are only for radial distribution networks. And in the first slide here we have the table in order to jump from our proposed model to Karamanis' model. And in the next one we have the tables in order to jump from Karamanis' model to the inscribed box model. And in order to prove this one-to-one matching, basically any point of a feasible domain of the inscribed boxes matches a feasible point of Karamanis and vice versa. The objective functions are identical as I showed before, and we have a result of the same optimal solution. To analyze a bit more our model, we have some simple two-node examples and understand the price formation that are forming due to congestion. In the first example, we have, as I said, the two-node network. The first node, the T node resembles the transmission net, the transmission side. The D resembles the distribution side. We have a BSP 1 and 2 in each node. BSP 2 it's cheaper than the BSP 1. We have reserve scarcity on the transmission side. So we're expecting an energy flow from D to D because there is a load here. So the energy flow is going this way also because we have reserve scarcity and the line capacity is maximized. We have a congestion caused in the line, resulting in price separation. The price pattern that we observed are that in the transmission side we're going to have the energy price equal to marginal cost plus the RDC adder, and on the distribution side it's going to be only the marginal cost. The second pattern that I want to discuss is if the energy flow and the reserve flow have opposite directions. In this case, we have just transferred the cheaper generator in the transmission node and the load on the distribution. So the energy is going to flow from top to bottom, and the reserve flow is going to stay from bottom up. In this scenario, the patterns remain the same as I showed in the last slide. So we're going to the next scenario. In this scenario, we actually modeled a downward reserve demand from the TSO. So the reserve flow is going to flow from upwards to downwards, from upstream to downstream. The energy flow in this case is going to flow from downstream to upstream, causing again a congestion, which is caused by reserve in our scenario. The price separation leads us to these two patterns, which in the transmission side it's going to be the marginal cost minus the RDC adder, and on the distribution side it's going to be the energy price, it's going to be the marginal cost only. And finally, in the case where we have the energy flow and the reserve flow in both directions, in the same direction, the patterns remain the same also. Okay, so in this section I'm going to talk about how we managed to create this mesh network that we were talking in the introduction. At first we have the transmission network of Belgium here. This data was taken by Bialek and et al. And was updated actually by our team, the Belgian team actually. Next, we have the topology of distribution networks that we used in our creation of network synthesis. On the left side, we have the network we call DN1, and it's based on Xanth's distribution network, and it's most of the time congestion-free. On the right side, we have a distribution network from Northern Europe, which we call DN2, and it's really prone to congestion. So what we basically did was we had a distribution network. We took the root node of the distribution network and just attached the root node to the and replaced the transmission node on the Belgium. And to expand a bit more, we applied the maximum spanning tree algorithm to each distribution network in order to gain radial distribution networks. And the maximum here is in order to keep most of the capacity of the network, most of the line capacity of the network, and not change as much the topology. And we duplicated arbitrarily as many networks as we wanted. In our case, we had 5 DN2s and 1 DN1. And this is completely arbitrary. As I said again, we replaced each transmission node with the whole distribution network, and then scaled each distribution network according to the load of each replaced transmission node. Note here, this was done for a certain time step that we chose arbitrarily again, and the scale factor was multiplied to the line capacities, the generator min-max capacities, and of course the load profiles. So this is the result of the final Belgian TNT network. We have 1,533 buses, the same number of edges. The highest voltage was 380 kilovolts, and we have a total of flexible assets of 59. The assumptions we made for our case study was that we had 8 day types, 1 weekday and 1 weekend per season. Each day type had a load profile and generation profile with 96 time steps. We applied also, again, a scaling factor for the distribution networks. We accounted only for the faster type generators to offer reserve. Line capacities of the transmission network were not considered. Imports of Belgium and hydro reserve offers were modified as positive injections of energy and reserve respectively. We introduced 6 RDCs per season, 1 for every 4 hours. The data was taken by Jacques, who has done extensive work for reserve demand on Belgium. Generator ramp limits were also introduced for reserve supply, and the unit commitment was pre-computed for each hour. So now let's suppose an investor is considering construction of a unit capacity of 1 megawatt with investment cost of €5 megawatt hours, which is representative of a flexible natural gas unit. We investigate the viability of the investment under 3 policies. The first policy is when the result reliability and scarcity pricing is not considered. The second one is when scarcity pricing is considered but not deliverability is considered. The third one is when both deliverability and the scarcity pricing are considered. Moreover, we examine the incentives of building the facility in different areas in our mesh network and considering alternative levels of flexibility, and to be exact, 10% and 75% of the installed capacity of the generator. The areas that we examine are the transmission network, the distribution network 1, which is congestion-free, and the distribution network 2, which is prone to congestion. Finally, the profit maximization problem of the investor at time step T is a very simple maximization problem of profit, which is the LR, which stands for the reserve price of the time step T, multiplied by the reserve offered of the generator, plus the energy price minus the marginal cost of the considered asset, aka generator. In our case, it's €80 per megawatt hours, multiplied by the production of energy. these are the constraints of the generator. So the prices for the first design, which we don't have scarcity pricing or reserve deliverability, we can easily say that there is a unique revenue stream only from the energy market. And the average price over the year was 21.96 euros per megawatt hour. For the second design, where there is scarcity pricing but no deliverability, the average price is again 21.96 euros per megawatt hour, and the average reserve price over the year is 10.36 euros per megawatt hour. It's worth noting that also the scarcity was observed during winter, while in the autumn we had zero scarcity. Finally, for the last design, where we have scarcity pricing and reserve deliverability, we can see an increase in prices, both for the energy price and the reserve price. This is caused due to congestion caused by reserve flows, which basically says that the DNFSPs cannot deliver their reserves to the transmission network due to the congestion in their area. And in general, this means that we offer less reserve, so the prices go higher of the reserve. Next, we're going to talk about the profitability results for the asset when building it in the three areas that we discussed. First, for the transmission network, when the asset is inflexible, here with the yellow color, it's the design one that we talked about that has zero scarcity pricing, that had no scarcity pricing and no deliverability considered. The blue color is the design with only scarcity pricing, and the orange one is the design with both scarcity pricing and reserve deliverability. The gray bar indicates the investment cost. So when the asset is inflexible, the investment is not viable under any design, as we can see here. And also for the yellow policy, we can clearly see that it's not worth investing under any flexibility of the asset. Lastly, when deliverability is considered, you can see profit of the transmission network increase quite a lot due to the increase of the reserve prices. So in the second slide here, we see that we expect that the absence of congestion in the distribution network 1 will result in the same prices as in the transmission network. And also the same outcomes will come as in the case of the transmission network. Finally, for the third design, for building the asset on the distribution network 2, where we have congestion. In this case, when we have a flexible asset, when we're trying to build a flexible asset, design 2.3, which is the orange one, decreases the profitability of the flexible supply of the FSP because reserve cannot be delivered at the transmission network, and it is not paid for that. In the case of the inflexible asset, it is very interesting that the investment here for any design is worthwhile because of the local congestion. Basically, what happened here is that due to the local congestion at the distribution network, a pretty expensive FSP activated and causing the prices in that area to go high and the profits also to go higher. This is in contrast to the transmission network results for the inflexible asset, as we saw. In conclusions, we propose a formulation of reserve deliverability using an inscribed boxes formulation. We establish the equivalence of inscribed boxes formulation and an alternative formulation based on Karamanlis-Hogan. We analyze the properties of the DLMPs resulting from our proposed model. And finally, we simulate results on a realistic case study of TNT coordination in Belgium, and concluded that accounting for reserve deliverability can enhance TN reserve prices and discourage investment in assets sitting behind the DN congestion. And scarcity pricing can encourage investment of flexible assets in a tight system, as we saw in the last slide. Thank you for your time. Questions?
Thank you, Ran. Any questions for our speaker? Yeah, Jack.
Thanks, Ron. Jacques Cartavez from UCLA. I'm not sure I catch that part, but so you have an RDC at each transmission node, or
Yeah.
okay, and then do you need also reserve in the distribution network?
No, only reserve. We offer reserve from a BSP that's producing, and only the demand for reserve is only at the transmission network node.
Okay.
So yeah.
Thanks.
So the transmission is anyway, we lift the capacity limit, so it's one ORDC anywhere in the transmission system, but can be partially covered by FSPs at the distribution system. So,
Okay.
So the name of the game is to figure out when they should and shouldn't be paid, but also accounting for the potential congestion of the line from the commitment of reserve.
Yeah, thanks for the talk. So, Quentin Leté, Zurich. So, I have a question on the network constraints. So, you said you at the distribution level, so you linearize them, right? So, is it a DC formulation or okay?
It's a DC formulation.
So, I wonder a little. So, you don't take into account like voltage constraints and stuff like that.
No, currently no.
Okay. Do you have some plans to expand this? Do you think it might influence in this kind of setting?
Do we have plans? I think we have plans to expand.
We have Lina in the back
Yeah.
who is looking in Bolognani's formulation, which I don't know if you're aware because Dörfler was involved in, at least gave some input to that. So Bolognani's formulation is just a mapping from injections of real and reactive power to voltages. It's a linear mapping, which is already interesting. The question is what you can do with that beyond power flow, and in particular optimal power flow. So we have then tried to use Taylor approximations to go from voltages to real and reactive flows on lines in, again, a linear mapping. Now, we may be making mistakes somewhere along the way because we are getting some mismatches between kind of non-linear power flow versus the linearized, and they're quite gross errors. So we're still looking into whether we've screwed up something in the reading of the paper and the implementation of the code, or if the model, he offers some accuracy guarantees, but in practice it doesn't seem very accurate. So we're wondering if that's just our mistake or if there's an issue with the model he proposes. But if we can pull that off, it means we now account for voltages, not losses. I think it's a lossless model, and I think I'm correct in saying that, but at least voltage limits, and you can also do quadratic convex constraints for apparent flow limits. And that then is an enhancement. And that can be kind of plugged into Ran's framework.
Dimitrios Glinos, TU Dresden. My question is, can you also consider grid congestion management to alleviate congestion at other transmission points?
For this case study, we didn't include the transmission line constraints, but I think it would be viable if we applied the constraints.
And do you expect similar results?
Similar results. If for building like an asset behind the congestion and the transmission, I think we will expect similar results. The price behind the congestion is going to be absolutely zero for the asset, for building an asset there.
One thing to add to that is basically what we're doing and what Karmanis had proposed with Hogan on a radial network there's no advantage. It's equally heavy what we are doing as what Michael was proposing. Where we have an advantage is when you have, it's the figure that Ron showed in his presentation, where you have different bidding zones with different reserve requirements. There we get away with a single set of power flow constraints, whereas Karamanlis would need an exponential number of power flow constraints because he needs to look at the combination of all possible patterns of activation. TSO1 doesn't activate anything, and neither does TSO2. TSO1 doesn't activate anything, and TSO2 activates fully. The opposite, and then they both activate fully. And in a mesh network, it's important to be able to get away with one set of power flow constraints as opposed to 2 to the n. I think we are restoring our original time schedule.
Yeah.
Great, thank you, Ron.
Okay.